As a music person, I got to have a mic in my hand, right? So I took some paper and some masking tape and got rid of some of the trash and made myself a microphone. So I'm good to go, right? So I want to talk today about music is math with feelings. And I want to begin with a reference to the song More Than a Feeling by the band Boston. You familiar with that song? Well, the chorus says, more than a feeling, when I hear that old song they used to play. Well, in my imagination, I like to think that the lyrics are a little different than that. I like to think of it as more than a feeling, it's math with feelings. Because it's really true that music and math are deeply intertwined. For example, the chord pattern leading into the chorus of this song is very famous and very catchy, and it was coming through the sound system earlier today, but we're going to try and see what happens. Let's take a listen. It's gone. But those of you that know the song, you probably recognize the chord pattern, right? So most of us, when we hear it, what we hear is dum da dum 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 da dum da dum, right? Right? A little air guitar thrown in on the side, right? Okay. Well, see, that's not what I hear though. What I hear is 1 1 slide up to 4 6 my minor 4 5 4 whatever it is written right there, right? That's what I hear, though. What am I referring to? When I listen to music, I listen to the numbers of the chords, called the chord numbering system, where every chord in a scale has a number based on where that root note falls within the scale. For example, here you have the C major scale, okay? 8 total notes, but really only 7 different notes because the C repeats. If I were to build a 3-note chord onto each of those notes, I get 7 chords. 3 of them are major, 3 of them are minor, and 1 is diminished. And this pattern holds for any key, as we see here. Here we see a variety of keys, but all of those keys, the 1 chord is a major, the 2 is a minor, the 3 is a minor, and so on. So in the first line, we see the C major scale chords that we saw in the previous slide. But if you want to play along with Boston in a real guitar and not an air guitar, you're going to go down to line 5, and you're going to play G, G, slide up to C, E minor, D, D, C, G, because you're playing along with Boston in their key. But the beautiful thing about the chord numbering system is it doesn't matter what chord, what key you want to play in. If you know the numbers of the chords, you can play any song in any key. That's the beautiful part of the chord numbering system, our first connection to math and music. But the math and musical connections do not end there. In fact, the history for the scale itself can be traced back to Pythagoras, because it was the Pythagoreans that taught us that musical pitches are defined by mathematical ratios. Did you know that? If you take a string and stretch it out and pluck it, you'll get a tone. But if you cut that string in half and pluck it, you will get the exact same tone an octave higher. So a 2-to-1 ratio, or a string length of 1/2, produces an octave. And here we see 13 different Pythagorean ratios that make up the 13 notes of the chromatic scale, which is really the major scale, the 8 blue lines that you see there, that we saw in the key of C a moment ago. But the white lines are the 5 passing tones in between those. And furthermore, it is these exact same Pythagorean ratios that define where the frets go on a guitar. So I imagine it as Pythagoras was the very first rock and roll guitar hero. Yeah. This fact is such a famous part of our math and musical history that it's even been celebrated by the Donald. Yep, Donald Duck in Math Magic Land. Celebrated with the Pythagoreans, right? So Pythagoras is definitely my choice for lead guitar. So who's on keyboards? Well, for that, we're going to look to Fibonacci in his famous sequence, right? 2, 2, 3, 5, 8, 13, 21, starting with 2 1s, right? Okay? Well, to see the Fibonacci sequence, let's look at his typical keyboard, all right? But to see it more clearly, let's look at 1 octave of the C scale, like we've already looked at, right? But here we have 1 octave of the C scale. I don't know what you see when you look at that, but I'm going to tell you what I see. I see 2 black keys, and I see 3 black keys making up the 5 accidentals within the 8 notes major scale, and when we put them all together, we get the 13 tones in the chromatic scale, or 2, 3, 5, 8, 13. Not only is Fibonacci on keyboards, Fibonacci is in the keyboard. So I've got Pythagoras on guitar, I've got Fibonacci on the keyboards. To round out our great band, as with any great band, we need a great drummer, and for that we look to Euclid. Okay? In 2005, Godfrey Toussaint from McGill University in Montreal wrote about the connections between the Euclidean algorithm and musical rhythms, among other things, including some things in nuclear physics and chaos theory. Crazy article, but I'm interested right now in the musical connections. In short, Godfrey was talking about a way to use Euclidean spacing to space a certain number of objects equally within a certain number of spaces. And one example of that is the Euclidean 3/8 beat. We can spread 3 beats as evenly as possible over 8 spaces. Visually, it looks like the 1, and then the and after the 2, and then the 4. But musically, this is the dotted quarter note, 8th quarter note tie, quarter note pattern, which Toussaint identified as the Cuban Tresillo, or American rockabilly, made famous by Elvis in Hound Dog. You ain't nothing but a hound dog, right? Rocking all the time, right? So that is an example of a Euclidean beat, and so Euclid is definitely my drummer. So I began this talk today with my imagination regarding the lyrics of a song. Now it's your turn to imagine. Because I'd like you to imagine Euclid on drums. I'd like you to imagine Fibonacci on keyboards, Pythagoras on lead guitar, and yours truly out front. I like to call us the Euclidean Fibonacci Pythagorean Sword Play Band, or EFDSPB, which kind of sounds like F, Pazipaba, F, Pazipaba, F, Pazipaba, F, Pazip. Well, you get out a pen and make a segment of a line now. Don't be afraid, you're about to use your mind. That's okay. If it ain't too clear, we're going to work together, and we'll start right here. Now, scribe another little segment of a line, but it goes right here and make it just like mine. Connect these two and just hang loose, and then call this the. You never heard that in a rap song, have you? No, that's what I'm talking about. Now take the side length here and you call it A, and you multiply A times A. Take the side length here and you call it, and you multiply. Yeah. Take these two and you add them up, and I'm on a roll so I won't shut up. There's another side we still can see, the hypotenuse, and we call it C. Now take a look at what we got. We got a right triangle, and it's really hot. That's what I'm saying. Yeah. Do you see that C? Don't be confused. It's just the length of that. That's twice. I rhymed it. Now here's the truth, and it really works. I'm telling the truth because I ain't no jerk. C times C, it equals this. It was proven by. Because it's F Pazipable, F Pazipable, F Pazipable. More than a feeling, it's math with feelings.